guys, today I'll show you how to make your own machine learning model from scratch using Python. So if you want the code, they're on my GitHub page, coding stick. And first of all, you need to import libraries like and then when you're done, we're gonna be making our own data instead this time. So let's say our problem, there's a farmer and he's selling these melons, and we want to predict how the size of a melon relates to the price it's going to, for example, $10. So our x value is going to be the size of a lemon, and the unit doesn't really matter, and our y value is obviously going to be the price of the melon. This is a really simple project, and we only have one type of feature, and y is going to be our label we're trying to predict. So we're going to convert it to data frame because it's the standard for visualizing data in machine learning, as you can see here, and I use it in many of my projects, so we don't really need to reshape it. And we have a NumPy array right here for our features and labels. So the basics of it is that we have a bias and a weight, and we multiply this weight by the x value and we get the y value. So we can train the model on these two, and the model needs to learn these two parameters. In other models which are really large, we get like more than one bias and more than one weight. So we also have W2 like that, and we're going to be using something called gradient descent. We can plot this like that, and we can see these are our data points. Change this up quick. Yep. Okay, that's good. And actually, so we need to fit a line through these points, right? And so we're going to use something called gradient descent, which is basically, this is our line, and we can find the error of the line using this. Basically, you draw a line down to that line and find the distance, and then you square it. You get something called mean squared error, which is the benchmark for finding how much the line is off from its actual data. And obviously we want to minimize this, so we're gonna go through a loop, and every time the line gets more and more fit to our data points, so eventually it corrects itself to the actual data. So the math of it is pretty complex, but this is the equation you'll need to know. Alright, so first of all, we need to initialize the bias and the weight. You can set these to any random numbers because the model is going to learn itself. So I'm just going to set the bias to 1s and the weights to 0. Alright. So this is our x before the bias, and this is our x after adding the bias. So it makes it into basically 2D array with just one above. Alright, so let's say we have this array and we have the bias and the x, right? What we can essentially do is multiply this by our weights. In this case, we can call it theta. It's gonna output an array of prediction. So we call this our y hat, which is the prediction, and we can calculate the error by taking this minus the actual data points. So y hat is the prediction and y is the actual data. So we get the error of that. And using this error, we can use our complex math equation to predict where we're gonna move the line next. So let's say it predicts that the slope should be a bit bigger and the bias should be a bit smaller. So let's say this, yeah. And then we run, and then since it's in a loop, it's gonna run again and find the cost of all these guys and do the multiplication all over again, find the cost function all over again, and we keep doing that until whenever we want. This is our main loop. So the learning rate is basically how fast it's learning, and epoch is how many times we're gonna run this loop. So you can imagine the gradient descent function as a little curve like this, right? And this is error, how much error it has, and these are the parameters. So let's say we want minimum error, like here, and this is where we started. So what the gradient descent function actually want to do is go towards this downhill. So it calculates this direction and then it takes a step in this direction. So think of epoch as how many times, how many steps it takes. And learning rate is the size of the step. So if you take a step too big like this, you might not get to the desired direction. But if you take too small, it's gonna take forever to get to where you want to be. And so you want to find the perfect number of epochs and learning rate. So I started out with 0.01 and 1000 for epochs. We're gonna find our prediction using dot product of data and theta, and then we find the errors using predictions. And then now we actually take the step by updating our value. For every 100 epochs, we're gonna print out our error value. For this function, we're gonna return theta. Let's run this. Everything looks perfect, and so these are the parameters that it learned, and this should be the bias, this should be the weight or intercept and slopes respectively. So to visualize this data, actually I'm gonna see, oops. Alright, so this is what the model learned, and as you can see, it's a pretty good fit. But I feel like we can optimize this even further. So what we're gonna do is try to plot the error rate over time. So what I'm gonna do is keep track of the theta, or the learned parameters, as the model trains itself over time. So what we need to do is add and now we can actually plot this. The loss started out at 43.6 and it decreases over time and approaches the value of 0 as our model gets better. Okay, so as you can see, for the bias, the error goes down and then it plateaus. Same thing with for the weight. It goes up to around 0.5 and goes back down to 0.25. What's the final one? 0.3 and 1.89. They both approach their final values here. And yeah, it's really easy to think of the analogy like the parabola, a person walking downhill, and as he approaches downhill, the closest point, he kind of plateaus because the error is like the minimum there. So now what I'd like to do is know what values of epochs and learning rates are the best, because I kind of want to optimize this. So what I think we could do is plot the error versus the mean square error versus the learning rate, and the mean square error versus the epoch as well. Alright, and we're going to be using a scroll bar to tune the parameters. So so we have these, and we can see it plateaus over time. So let's say we want to optimize the number of epochs for 2600 epochs, and you can change how smooth the curve is. Let's just do 20, and let's say we want to start at 0 and as much as 0.6. Okay, so you can see it really starts to plateau, and then it doesn't really get much better, and you can kind of see it more clearly here, I guess. Yep. And we can basically do the same thing for the epochs as well, instead of a learning rate. A little typo here. So let's say we want to find the optimal epochs for learning rate of 0.003, and so we can see it starts to plateau around 3000, right? And let's close in on this guy. Okay. No. Yeah. So I guess it's just fun to play around with, and it's really cool to see how the machine learning can kind of correct itself. Anyways, thanks you guys for watching. I'll see you in the next video.